All right. So I'll be providing a workshop on an introduction to Shiny. So making your own interactive web applications using Shiny. There's a bunch of different tools available for making web applications. But for people in the sciences, especially marine sciences, most people learn R for data wrangling, stats, all that kind of stuff, visualization. So this is a nice um, natural extension of being able to use R code to produce web apps. So what is Shiny? Shiny is a software for web app development. Like I said, that basically keeps you from necessarily needing to learn these other typical programming languages such as JavaScript, HTML, or CSS that are standard programming languages for web development. Obviously, it helps if you know these things, and it can actually be used to kind of enhance your Shiny apps. But you don't need to know it. All you need to know is R, essentially. And then behind the scenes, this R package Shiny does all the translation into these other languages for you. So, like I said, all you need to know is how to code in R. And then this past year or so, they've also released a version for Python. So for people that also code in Python, that's an additional option as well. And these web apps are often run either locally, so just meaning like on your computer that you're using, online, so remote. And this could be on a number of different websites, or could be served as part of an R package. So you could build a Shiny app as part of an R package, and then make that available for your team or the larger public to install and then use as they see fit. So there's a large number of reasons why you might want to be interested in creating a Shiny app. These could include data exploration. So you get a bunch of data and then you go through a workflow of just exploring it, doing some QA, QC on it, something to that effect, just seeing what your data look like initially. Additionally, you might be interested in collecting data. So this might be something where you're either eliciting expert information, maybe you're doing a survey, doing something else that's interactive. So you might be kind of having different people using your app, and then they're submitting answers or results of some kind. Additionally, they could be used for sharing results of a study you just did. So in this example, this is green turtles throughout the Gulf of Mexico overlaid on top of sea surface temperature. So you can, I would assume in many cases, share your results through either maps or plots or tables, etc. And then another instance could be using them for decision support. So this is an example from EcoCast, where these maps might be used to inform decisions and kind of be used for stakeholders as well. But basically, especially for decision makers making management decisions, in this case for the California current ecosystem. So Shiny apps could be good solutions for many different projects, since they are one, free for end users, so you don't need to pay to access any materials for developing a Shiny app, or the people accessing your app don't need to pay to use it. It's also cross-platform, meaning it could be used for different devices, which that's either phones, tablets, laptops, desktops, works on all those different devices, as well as different operating systems. So Mac, PC, or Linux, it doesn't matter what type of computer you're using. They all will be able to access and use these apps. And then lastly, they're easily accessible to people without software installation or knowledge of R. So if you're interacting with stakeholders or the general public, I would say that most of these people don't know how to use R. Maybe they know a different programming language. Maybe they don't know any. So especially if you're sharing these with decision makers, it's really nice to have a Shiny app or a web app in general where they can interact with it online without needing to install anything or have knowledge of computer programming. So how does Shiny work? Well, at its kind of most basic components, there's two different parts to think about, and these are the user interface, also shortened to or abbreviated the UI or the front end. And then there's the server, and that's like the back end doing all the heavy lifting. So I really like this kind of diagram schematic by Danielle Navarro, showing how this works. So on the right side, we have the user interface that's being drawn or displayed by what's called the client. So this is basically just your browser. So the user interface is what the users are directly interacting with. So this is the plots they see, the widgets, the inputs that they're interacting with or changing. That's the entire like, user experience is interacting with your user interface. But behind the scenes in the background, what's producing the plots, what's changing inputs, what's doing all these other things is what's called the server or the back end. And in this case for Shiny, it's running R. So it's doing different computations in R and then updating these plots or these inputs based on these changes. And when you're first doing this, as we'll be doing today, this is just done on your computer. So your computer is serving as the server. In this case, it's what's doing all the computations. But unless you have your computer open all the time, other people might necessarily be able to access this if you want to be able to share it with others. So a more reasonable solution to this, especially for sharing Shiny apps more broadly, is through deploying your app to the cloud in some format. And there's a bunch of different cloud app services. And if you deploy to the cloud, then you're basically using other people's servers to do all the work for you. And then all the a user needs to go to is find the URL where your Shiny app is hosted. And then the Shiny app works every hour of the day as long as it's being deployed and hosted without any issues. So this is kind of ultimately where we're going to get to by the end of the workshop is deploying a Shiny app to the cloud by like a RStudio Posit kind of free service essentially. All right, so again, based on how Shiny works, I just talked about the UI and the server. So we'll look into this a bit further, looking at the code specifically. So this is a really simple example of a Shiny app. First, focusing on the user interface. The only thing I'm loading in this case would be is the single Shiny app. So hopefully that is installed if you'll be following along for today. And then we have some simple boilerplate kind of code here. So the first thing I'll focus on is the title. So using this title panel function, I'm specifying this title Old Faithful. So the data we'll be looking at in this particular example is the wait times between eruptions from Old Faithful, which is, I think, pretty timely given the recent incident at Biscuit Basin in Yellowstone a day or two ago. This is a pretty common example that's shown for learning how to make Shiny apps. So yeah, this is defining the title. Next, we have our slider input. So this is an input widget, and we give the widget here an ID labeled bins in this case. This could be anything you want, but ideally something that's easy to remember and kind of apt for this particular input. So the label, so this is what the user is reading in that user interface. It says the number of bins. So this is more like people, readily, like easy to read. And then the input ID is more for like the computer. So it's something that's typically short and doesn't have any like, special characters involved. Also specifying here the minimum and maximum values of this slider. So I'm setting these to 1 and 50. And then value here is specifying what's the kind of default value that's being set for this slider when it starts. And then lastly is the output product. So we have a function here called plot output. So this is what's plotting the output of whatever the object is. And the name that we're specifying here is dist plot. And again, this could be anything you want. This is the input ID for that particular plot. We go over to the server side of things. So the UI is an object in R, and the server is actually a function. So that's how these two differ when you're coding them. And within this function, you have to specify basically this exact syntax where you give the input, output, and session. And then you have your curly braces here. And then this is where you're going to enter all the info of what R is supposed to be doing behind the scenes. So the first main part of this, we have where we're storing our output product. So you see here at the top, there's input and output. So for output, we're using this $sign syntax, and we're assigning the variable dist plot that we had labeled here for plot output. So we're assigning to this variable dist plot a plot here that we're rendering using the render plot function. And whenever we're using like a render function for Shiny within the server, we have a parenthesis and then a curly brace. Then within the render plot function, we're loading the data, and then we're defining, in this case, how the bins are being broken up or decided. So we're having a sequence of the wait times from minimum to maximum wait time. And then the number of bins is being influenced by that slider inputs that we showed before in the user interface. So we have a number of input bins, and then we're adding a value of 1 to that.
Yeah.
And then the last part is making the plot. So in this case, we're drawing a histogram of this data set weight, and then the number of breaks are the number of bins here, and then we're just specifying the aesthetic, so the color and the border. And that's all we need to basically create just a simple Shiny app. So this is essentially what that would look like, is we have this single plot here with a slider, which says number of bins. That's the label for the slider. And then we have our output here, which is showing the histogram of wait times. And then I can just drag this around and it'll just update for me. So at its simplest, this is what Shiny is doing. It's just taking user inputs and then showing outputs based on those output changes. So,
Hey Josh,
yes.
would you be able to give people a sense of how much, if they already know R, how much code is new in the server versus the UI section that's Shiny specific?
Yeah. So I would say in general, unless you're doing a lot of kind of crazy stuff, that the UI tends to have less in it. Because you're just specifying maybe where things are placed. So in this case, I have a sidebar layout. So I have a sidebar area, which is where those inputs are, and then the main panel is the output. And beyond this, it really won't change much once you set that up. Whereas for the server side, depending on what you want to do, if you're doing a lot of filtering, loading different data sets, making different plots, the server could get really large. So there'd be potentially a lot more going on for the server, but this is, I would say, more similar to standard R code versus the UI. You're using like widgets and other types of functions that you probably aren't familiar with. So you would need to learn what's available. But there tends to be more, I think, code within the server components. Does that answer the question?
Yeah.
Okay. All right. So in addition to the user interface and the server, there's one kind of last component that's really important, and this is the use of reactive expressions. So the whole reason that we could change the number of bins for this histogram is because this input is reactive. So whenever the input changes, the output changes. And this could be used in a couple different ways. But yeah, basically the reactive objects are automatically updating the state of this app. So one example of showing this kind of graphically is this really nice GIF that I found from this React blog R package. But basically, this is a simple graph relating inputs on the left to kind of the values taken from those inputs, doing something with them, and then creating outputs on the right side. So each of these different shapes represent a different like object along the path. So on the left side are those inputs, whether it's a slider or drop down or whatever it is. And the right side is either a plot or text or something to that effect. And everything in between is probably like an R object. So when it's green, that means that everything's good, the values have been calculated, and then everything's shown or plotted or printed to the user interface. But when it turns dark gray, that means we're changing one of these inputs. That means we're invalidating it. And that's going to affect everything downstream. So everything else turns gray, as you'll see here. And that means that we need to update everything else. So we got to go back to the beginning, and then it turns yellow. So that means it's recalculating these values and then updating the output. And then it'll keep listening for any changes to the inputs, and it'll do the cycle over and over. So once you've made a Shiny app, most of the time you want to share it with other people, either in your lab, on your team, more broadly. And there's a couple different ways that this is typically done. One is through using a set of files, so maybe like a single R script that stores the app in its entirety, and then maybe a single data file, like a CSV, that you could run locally on a computer. So you can either do it yourself, or you can like email these to a collaborator, and they could run this in R on their computer. So that's one way to do it. Another way is to deploy it on an online server, like I mentioned before. And this is kind of the approach we'll be taking today. So we'll be using this website, shinyapps.io. And they have a free plan that you can use for deploying a handful of apps without needing to pay anything. There's an additional option that's kind of brand new as of this past year, and that's deploying Shiny apps using Shiny Live on essentially static pages, which I won't really go into because that's going to be on the scope of this workshop. But basically, instead of needing to deploy apps to this shinyapps.io website, you could just simply deploy it to a simple GitHub pages kind of like wiki page, because the server component will be the browser. It translates everything that would be done in R code essentially into JavaScript, which is how the web and the browser interface typically works and runs. But again, that's kind of beyond the scope of today's workshop. And additionally, you could even have apps that are built and deployed online, but then maybe you want to embed them somewhere else on like a website related to a certain project for NOAA or UC Santa Cruz. So you can do this, and I mean, typically one way, but this is I have a web page for a project I worked on a couple of years ago related to green turtle movements. And then I have on this a Shiny app that'll load eventually. That's embedded on this web page. And it's just because this is taking a lot of time, that's just demanding on the net. There it goes. Okay, so here's a track of one turtle for 1 month of the year. And then to show that it's reactive, I can change the month, and this will slowly, there goes update. And then you could change the region if you wanted to, and that'll also update. So yeah, you can embed this in a separate website instead of just that shinyapps.io webpage. Here's a list of additional resources for creating Shiny apps. This Mastering Shiny online book is really useful by Hadley Wickham. So highly recommend that. Something else that's new that's really cool that I haven't really played with yet is the Shiny UI editor. Essentially, you just go online here, you can download the package and build the user interface instead of through a code where you're dragging and dropping different components, and just lay out everything the way you want it. And you can just see it and everything without needing to manually kind of change code, then run it each time. And whenever you're happy with it, it'll print out the R code for you and just copy and paste that for your R script. So I think this is a really cool way to do this, and kind of lowers the barrier to entry for making different user interfaces for people that are just starting out. And the last thing, what was that?
Oh, you're just saying how awesome that is.
The last kind of link I'll show is just for other examples of Shiny apps. So there's a Shiny gallery from our studio Posit team. So as just simple examples here, like the Old Faithful example I just showed, it has kind of more interactive, complex examples. It has examples for just different types of widgets that are available, different types of inputs, ways you can adjust layouts for the app, dynamically updating the UI based on inputs that are selected, all kinds of stuff. So this is, I think, also another really nice resource for trying to figure out if you like a component of a certain app. It's like, oh, I want to have this side panel be semi-transparent and be draggable across the app. You just go to their source code and then look how they're doing it. So I think that's really nice. And then just other stuff here for putting Shiny apps in Cordo documents, deploying it to Shiny apps, which we'll be doing today. I was a part of a collaborative effort for running a webinar series with the Ecological Forecasting Initiative a few years ago, giving webinars on different components of running and creating Shiny apps. And then there's some other examples if you're interested in Shiny Live, once you kind of get the hang of using kind of the basic format for Shiny. All right, so that is the end of my slides. So now we're going to move on to the hands-on components, to doing stuff in RStudio, which I'm assuming is what most people are using for their coding. So I'm going to now, I guess, just share my whole window. Okay, so to kind of motivate what we'll actually be building today, I'll just show you really quickly the apps that we'll be building in kind of their final form. We'll be building two different apps. So one is based on the Palmer penguins data set. And we can basically build something and we have multiple pages. So maybe like an about info page as the landing page. And then we get to the data and we have it all nicely themed and laid out. And part of this is impacted just by the size of the window. But we can build something like this ultimately. And then for a different example, we could do something with a spatial component. So let's say we build a app that has different spatial layers. So we have polygons, we have lines, right, tracks, we have a raster layer, and these can all be updated and you can change base maps and all that kind of stuff. So that's the other app that we'll be building for this workshop. And all that code is available again in that zip file that you downloaded. Okay, so assuming you downloaded the zip file, what you would do is open it up, and then inside of that, click on the intro to shinyworkshop.rproj file. So that's an R project file that should just open up RStudio and then have all of this stuff in there, and you'll be in the right working directory and won't need to worry about anything. So just double click on that and it should just set you up to get going on this. But if there's an issue as you're doing this, if you're following along, then just let me know. But hopefully that'll just take you to RStudio and have everything kind of set up in your files window. All right, so assuming everyone was able to do that, we don't have any problems. I'm going to start with the Palmer Penguins Shiny app example. But one thing I wanted to point out really quickly is I have in kind of this main folder, I have two R scripts, skeleton app.r and skeleton app bslib.r. And these are just kind of templates for you to use if you'd like, for building the user interface in the server, either using like kind of standard Shiny syntax that I showed in that set of slides, or if you want to use the bslib R package, it has some nice functionality for building user interfaces that look a bit nicer. And I think the functions for putting this together are a bit more intuitive based on the names of different functions or their arguments. So I've been leaning more towards using bslib to do my kind of UI structuring, but I have examples for both of those here. Okay, so I'm going into this Palmer Penguins example folder within that larger parent folder, and then I'm going to start with this first file called simple app. And I'm using 4 different packages here to start. And these are Palmer Penguins, which has the data for this app, ggplot2 for plotting, Shiny to do all the work for running the Shiny app, and then bslib for kind of structuring the user interface. Is everyone able to see this RStudio window relatively well, or do I need to increase the font size and like make it larger?
Maybe a little bit.
I could be, yeah, larger.
Is that good?
Yeah. Roughly.
Mm.
Yeah, that's good. Is that good, Eunice?
Yeah.
How's it back? Yeah, I mean, yeah, okay.
All right. So you essentially load all of these, and then I'm building in this user interface. So actually, I have, do I have something going? Yeah, running the slides. Close that. So for the user interface, I'm calling this object UI, and I am using this page underscore sidebar function. So within that, I have the title that I'm assigning Penguin's dashboard as the title I'm giving it for the app. And then using the argument sidebar, I'm using a function called sidebar to build a sidebar. And you could give a title to that sidebar, which in this case I'll call histogram controls. And then now I'm adding a couple widgets. So one is going to be a drop-down selection using bar select inputs. And if you want to look at more of like what inputs are available, I would go to that Shiny Gallery website I kind of previewed before, and now I'll give you examples of what these look like and what they're called. So this is just kind of a standard drop down where I'm giving the widget an ID for the computer, and I'm labeling this bar for variable. The label that people will see on the UI is going to be called select variable. And then the data that this input widget is pulling from is essentially any variable, any column from this Penguins data sets that is numeric. So just for an example of what this looks like, we have a column for species, islands, and then different morphometrics. So bill length, bill depth, flipper length, body mass. And then not shown here are sex and year. So we only want the columns that are numeric to be available from this dropdown. And then in addition to that, we have a slider input like I showed in the slides for that Old Faithful example, where again, we're labeling this bins, number of bins, setting the min and max values, and then the default value for the slider. I'm setting step equal to 1, meaning that I want the value of the slider to change for every integer instead of, I think by default, it might be larger than that. So you wouldn't be able to choose any of the values, only some of the values on that slider. And then I comment out a lot of times when I'm closing sections off, just because this can get messy really quickly. So I'm closing the sidebar here, and now I'm moving on to the kind of the main panel. So this is where all the output is going to be plotted or added. And there's a function from BSLeg called card, and that basically adds this like kind of block box where it's going to store your outputs. And I'm giving it a title using the card header function with histogram, and then the plot outputs I'm labeling hist. And to see what this looks like, just because I think that's going to be easier. This, there it goes. Okay. So this is the UI that I just kind of talked through. So we have our sidebar here on the left that has its own title. We have our drop down.
I am not going to
And slider. And then our card here is storing the histogram, and it's just kind of a standard base ggplot histogram. But if we were to drag the slider, then we get it updating, and we get these warnings in our console just saying that there's 2 rows of data that aren't available. I'm assuming they're just missing values. But we have a basic working Shiny app. So for the server components, this is super simple. It's basically the same thing I just showed in the Old Faithful example. So we have our server object, which is a function taking the input, output, and session. Session is just like everything going on during the R session. It's like what it's doing in between the input and the output. And then we have our single output here labeled hist, which is what's in this plot output function in quotes. So we're using render plots. We want to produce a plot. And then using ggplot, we give the data, so penguins, geom histogram to create a histogram. And within the aesthetics, we're providing input $var to get the variable selected from the dropdown. But we have this double exclamation points, often I think referred to as like a bang bang operator. This is used to remove quotes from the character string so that it's like properly rendered. And then we have our bin number of bins here. And that's it. And then at the very end, to run it, if you were to run it interactively, instead of pressing that run app button at the top, you run Shiny app function with UI and server inside of it. So to show why this bang bang operator is important for this single instance, if I just delete it and then run this app again, it's going to fail because it says in here, named vector, something about not being supported. Basically, yeah, it's not going to actually know what the value is for that character string. So you need to make sure that that is there in this particular instance. So yeah, that's the simple version of this app, and then we'll be building on different components of the app. And for the sidebar, there's this arrow here. So if you want to, you could hide that sidebar. And this is what's available kind of by default for BSLib. Okay, so that's it for that first script. We open up the second script. We have two more packages in here. So we have the dplyr package from the tidyverse for doing wrangling, the DT package for creating interactive tables, and then everything else should be the same. But I'm just going to restart R, just get a fresh session and environment, and then I'll just run the app to show what it looks like, and then talk through the code to show what is doing which components. All right, I got to make this a bit larger so that it actually shows up. Okay. So we still have our sidebar here, but now we have an additional drop down where we're filtering by species. And then in the main panel, we have our histogram again, but now we have it colored by island that the penguin species belongs to. And then beneath that, we have an interactive data table and then a kind of like text output from R, essentially. So for each of these cards, you can also expand these and make these kind of take up the whole app window if you want, which is nice. Especially for things that are kind of compressed here because I have the font size blown up. So for the DT tables here, there's all these different pages based on the number of entries or records. Here is 152. We want to show more, we can change this to 50 and you can scroll it. You can also sort. If I want to sort by islands, I could. If I want to sort by species, I could. If I want to filter, I can just search for something. So like, let's say Dream Island. So now it's only to show me penguin records where they were found and measured on Dream. And we show here at the bottom that there's 56 entries of 152 where they belong to Dream Island. So there's a lot you can do with DT tables. And for this summary, I just have an output of sample sizes essentially per species and island. So in this case, it's showing that the Adelie penguins were sampled or measured at 3 of these islands, so Bisco, Dream, and Torgerson. The chinstrap penguins were only captured or measured at Dream, and the Gen 2 were only measured at Bisco. So that's the general components of this UI that's being shown. And if we move over to the code, so a lot of it's going to stay the same. So I have the title just labeled inputs. For this first dropdown, I'm using the select input function. and then I'm giving it the label species, and then or the ID species, that's what the computer is referring to it as, and then the label that's shown here is filtered by species, and then the choices that are available for this drop down, I'm just using the unique function to only choose the unique species that are present. The var select input for the variable stays the same as before. So this is only the numeric columns within this penguins data set. And then beyond that, now we're kind of getting into a little bit more complexity with how we're going to lay out the content for like this main panel here. And this would be, I feel like, more difficult to read if we're using the normal Shiny functions for the UI. But for BSLib, if we use that for creating our user interface, we can use this function layout columns. So we can specify how much space they take up and where we want them positioned, essentially, especially if we're doing like grids. It's really nice. So I'm using this layout columns function and specifying the column widths and the row heights. So one thing that's important to mention here for column widths is that all of the user interfaces are essentially broken up into 12 equal columns. So this is just like essentially 12 units. So I'm saying that I want the first object of my 3 outputs here. My first output is going to take up 12 units, which is the entire row. So that's why we see this density plot takes up an entire row of space. Once we exceed 12, it moves it on to a second row, and then so forth if you have more components. So for the second row, we have our next component taking up 8 units or 8 columns, which is this data table. And then the last component, the kind of summary output, is taking up 4 units or 4 columns. And that's why it's the narrowest. So we can change this if we wanted to. So let's say I wanted the table and the summary output to be taking up even amount of space in terms of their width. I could change those both to 6, which sums up to 12. And then now you can kind of read that summary output a bit better than previously. But you can just adjust and decide how much space you want each of these to take up. And it's kind of just compressed here, I think, because I have, the magnification up. If I was to decrease the font size, it takes up less space and shows up a bit better. But I'm just trying to keep this zoomed in so you can read the code. And then for the density plot, I have this within a card like I did for the simple app example. So I'm specifying the title, which is density plot, and then I'm labeling this plot output as dense, just an abbreviation. And then I'm saying for this argument here, full screen set to true. And that's what allows us to use this expand widget to open up the plot here in this case to take up the whole app space. If I set this to false, it wouldn't have this expand widget available. For the table, I'm also putting this in a card. The card title or card header is data table. And then from the DT package, I'm using this function called data table output. So anything that you want to have shown on your user interface almost always ends with this output name. And then whatever's in front of it is related to the input and the package you're using, essentially. So in this case, it's a data table, and I want the output shown here for the UI, and I'm giving it this ID called table. Short, and this also I wanted to allow to be full screen. And then the last output component here is the text summary. And that's with this verbatim text output. So it's basically saying if I was to print something into the console, I wanted to print verbatim into this card, and then also allowing this to be full screen. Are there any questions on that at the moment, or something else that I might have just skipped over?
Is the TBL referring to something specific inside that function? Or is that
No,
something that
so
you,
this could be anything you want it to be. This is the ID name I gave it because it's just an abbreviation for table, so it's easy for me to remember. So this is what I'm going to be referring to in the server. So if I scroll down a little bit, I have output $TBL for table, and this is where I'm going to store that table once I render it. Same with the other names, output dense, and then output txt for text. These are the variables where I'm going to store the rendered objects, essentially.
thank you.
Okay, so for the server component, I'm going to start off by introducing the reactive expressions. So for the simple app component, we are just using input $, whatever the ID is for that input. In this case, we're now using reactive expressions, which give you more power and flexibility to do things. So I'm assigning basically the output of this step to this object called penguins_react. I'm using the reactive function from Shiny, which also requires this parentheses, then curly braces. And then within it, I'm taking the penguins data set, and in this case, I'm using a base pipe and filtering by species here. So based on the input, which I have labeled species for the ID, whatever that selection is from the dropdown, that's what I want to be stored in this penguins react object. And the thing that gets, at least initially, tricky or confusing is typically in R, once you store a filtered data set in an object, you just basically put that in the console or print it, and it just shows you what's in it. But for reactive objects, moving down to this plot, so we're using render plot here again. But for the penguins react object, we have to end it with open parentheses. And that's essentially, it's kind of treating it like a function. So if we don't include these open parentheses at the end of this penguins react object or any reactive object we create, it won't work and it'll throw you an error. So you need to remember to always include these open parentheses at the end whenever you create these reactive objects. Otherwise, the other components are just kind of standard ggplot here for the most part. So using geom density to create a density plot. We're using this bang bang operator again in front of input $var because we're trying to unquote the text string to use this non-standard evaluation from like tidyverse syntax. And then we're specifying the color palette and setting the text size here. So hopefully the ggplot code is at least familiar for everybody. You may not have used the DT package at all for creating interactive tables. So we're using the render data table function now instead of data table outputs. So for the server, we're using render data table to kind of produce the data table. And it just takes a simple data table function here. And all we're specifying is just the data set. So our reactive penguins react object. And that's all we're going to do. You can do more customization if you'd like. But with just the simple version, we still get a data table that looks pretty nice and has a lot of different features. So it's nice and simple to use. And then lastly, for the text output from the summary, we're just taking the penguins data set. So we're not using the penguins react object we created. We're just using the original penguins data sets. And then we're grouping by species and islands, and then using the count function to basically just come up with a sample size per species and island combination. And that's using the render print function in combination with the verbatim text output here for the user interface. And then that's it. You have the Shiny app function at the end holding the UI in the server, and that stores this entire app in 100 lines of code. So it's it's not too bad to add something that's relatively complex. This has all the major components you'd probably have in a standard dashboard. It just looks really plain because there's no theming or anything else that looks nice. So we'd want to add some other components to this so it's actually a bit more of a nicer user experience. So I'm going to open the third R script of this app. That's kind of the final version I showed at the beginning. And restart my R session. So I'm using the same packages as the previous script to the previous app, with the exception of now I'm adding the thematic package. And that's what's going to get us the nice theming across all of our different outputs. So before we had different components that might have like different colors for each of the rows in the data table. And maybe the background of the ggplot output would be white or gray or something else. But if we want the theme of the app, so the colors and the styling to all match all of our different outputs, we need to use this thematic package. So I'm just going to run this and then talk through the code. So one thing to note now that I have these components up is, in addition to just the colors and the styling, this app has two different kind of pages that are part of it. So based on the width of this window, let's see if it's gonna do it. There it goes. So it'll show both now that it's like wide enough. It shows this is the about page, and then there's a data exploration page. But if I decrease the width, it'll kind of put all these together into this like sandwich menu button, which then you can click and then navigate to the other page. So that's just something to keep in mind as you're working with this and putting something together and building something. It's going to like interactively update based on using some of the underlying styling programming languages like CSS. All right, so we can basically make this app with also not a ton of additional code from our previous app. And the first new component here in this script is using this thematic underscore shiny function. So thematic is what's keeping the styling the same across all these different components of this app, which now is like a multi-page app. So if I was to go to this page that has all kind of the data outputs, we see that the background and all the kind of theming and palette colors for the density plot all match everything else. So the data table is the same type of color palette, same as this output from R for this summary of sample sizes. So that's only possible by using the thematic function or thematic package. In this case, we're going to be using a custom font also. So I'm using thematic shiny, which that's all you would need to do. Just have open parentheses, but I'm using a custom font from Google Fonts. So I'm also setting font to auto, which should also now change all the main fonts here to match what I selected. And then we also still have our sidebar. It's collapsed because the width of this is smaller than what would allow it to be opened by default. Okay. So the next part, I'm just setting kind of the basic default settings for this whole app. For ggplot2, so saying I want to use the theme black and white and use a base text size of 16. And then now moving on to the user interface components. So I'm going to move this over. We have our page nav bar now. So instead of before we used page sidebar, if you want to use something that has multiple pages, one option for that is to use page nav bar instead. So we still provide this title here, Penguin's dashboard in this case. And then for our theming from the bslib package, I'm using this bs theme function, which you only really need to supply maybe one or two arguments. I'm putting this here just to be more explicit about which version of like Bootstrap I want to use. So Bootstrap is kind of the different themes that the bslib package uses. So there's a bunch of different like templates or presets you can pull from. And based on the version, there might be some that are available and some that aren't. So version 5 is the latest version. If you were to select version 3, which is the previous one, for some reason, it might not have all the different presets or template themes that are available. So in particular, I'm using the Vapor theme, which is what's with all these gnarly colors and this kind of dark theming for this app. And I'm specifying this from the boot swatch argument here. And then to add some custom fonts to the whole app for base font. So this is going to impact all fonts across your entire app within page navbar. You can use the fonts _ Google function and then just add in here the name of a font from Google Fonts. So in this case, I'm using Roboto. Moving on. So within a page navbar, you want to kind of specify the content per page. And this is done using the nav panel function for the most part. So for your title, that's kind of what's going to be on this nav bar that's going to show up is, in this case, about is kind of what I'm calling this info page. This could be anything you want, but you would specify it with title. So moving on from that, after giving it the title, this is where I'm adding all the content into the Shiny app. One thing that'd be nice is if you could just add kind of markdown text. So for anyone that's used R Markdown before or Cordo, you can specify a lot of the different styling really easily. And that's not available by default for like a Shiny app. So you need to use some of these functions, these essentially HTML tags available from the Shiny package. So this H1 function means it's a H1 header. So that's like the largest title header style that's available. And that's what I'm labeling here for Palmer penguins. That's the largest text at the top. And if we want more like a body of text or like a paragraph, we use the P HTML tag or P function in this case, and then just write out some text. So this is giving the info of like acknowledging where the data came from. And let's say we want a second paragraph. You might just end it there, add a new paragraph here with a new set of text describing the data set itself. And then I wanted to add in a link to Allison Horst's kind of GitHub page here for the Palmer Penguins data sets. And then also for really cool illustrations that she creates, in this case, specifically for the Palmer Penguins data. And that's done, again, essentially using R versions of HTML tags, of HTML code. So I'm specifying what the kind of text I want to be shown. And then with href, I'm specifying what the kind of hyperlink or the URL is that should be kind of linked to. So in this case, they're both the same. For the artwork, I'm using this image function. Source is telling the image function where this image is coming from. So if you were to right click on a picture somewhere online, it's a copy image address. It should give you a URL string, and then you could essentially put that anywhere you want, in this case in a Shiny app. So that's how I'm adding the image basically from online. I didn't even have to download it. I'm just referencing it inside of Wi-Fi. I have internet access. So that's everything. That's all the content on this first page. So we're closing that nav panel here on line 48. And then we're creating a new second page called data exploration, which is where all the data summaries and outputs are. And this is going to look essentially the same as before. So I won't spend too much on this component. Layout sidebar, defining these inputs. These haven't changed. These are exactly the same. The cards for the layouts. Yeah, so this is all the same as before. So it's all the other stuff up at the front, doing all the theming for us. All the content hasn't changed. And then server should also be the exact same. I didn't change anything. All I did was add a new page at the beginning and change the theming, the styling. And it all just should work. So hopefully for those following along, if you are up to this point that you were able to get something that looked like this actually show up on your computer. But this is the end of the first web app that we're developing. So I think this is as good a time as any to ask if there's any questions or problems that came up.
I guess I'll ask the question if we stutter.
Yeah.
How often, I don't know if it's bad practice, instead of, unless I have to define a reactive object, just do it all within like the render plot code, you know, like instead of having a separate object. Is there a reason, like, for example, on the O2 app, you could take the code that, you know, gets the penguin filtered data set and just types it right into the ggplot density plot. So I'm just,
Yeah.
like, is there sort of a best practices reason why you pulled out those two components?
Yeah. So for one thing, one of the main principles for like coding, computer programming is referred to by the acronym DRY, is do not repeat yourself. So in this case, you could just copy and paste this kind of throughout each render plot and it'll just work if you're using that particular data sets. But let's say you wanted to make a change, you want to add a new filter component to this or do something else. And let's say there's more than just 3 outputs. You're having to go through each of these and either like do the Control F to like search for it or go through it manually and do it. And it just introduces more potential error. So by having all these outputs rely on a single data source, you're kind of streamlining this a bit and then obviously reducing the amount of code on your script, which should make it easier to read through for you or somebody else, and make it easy to change and update. So in general, when possible, I would say kind of best practices is to like reduce the number of different components you're making, if at all possible, to fewer components that are kind of can be used across different outputs here in this case.
Yeah, that totally makes sense.
So if you wanted to filter it differently, would you create another reactive object?
So if, let me just pull up the app just as an example of what this would look like. So let's say we had the same app here, but we wanted to filter by species and by whatever, another like year. That we could add another drop down that says filter by year. And what we would do in this case is type year equals input year. And let me make sure that it's not uppercase year. No, lowercase. So I'll just literally copy and paste. Why is this going so slow? Year, filter by year, penguin year, that. And hopefully this just works. Just do it. Okay, so now I have a Delhi penguin in year 2007 by default. So if I change this to not 3 years, 2009. So if I open this up, I'm only seeing data for 2009 here. So yeah, it looks like it worked. And again, this output for the summary is based on the original data set. So this doesn't change, but the density plot does, because it's also dependent on that penguin's React object. So yeah, you essentially just do that, and then you can kind of limit again how much extra space is getting taken up by the code in your server, and it kind of just streamlines things. If you wanted to do something completely different, you would just need to create a new reactive object, and then that output would depend on that separate reactive object. Say if you had something summarized by year and another one was summarized at a like this finer scale, you maybe want 2 different objects available to use. All right. Well, I'm now going to move
I have a
on.
question.
Yeah.
So in layout columns,
Mhm.
I know I caught you talking about call widths being split up into units of 12.
Yeah.
And sorry if I missed this. Can you go over how row heights are split up? Like in this call, you have 1 and 1.5.
Yeah. So I just kind of skim through that, but essentially, it's just like ratios. So in this case, there's just like a lot of space taken up by these headers for the cards. And then for the table, there's like the filtering stuff at the top. So that's more space lost for the table content. And I didn't need as much for the density plot. So I wanted to make the bottom row taller. So in this case, I have these specified to 1 row height for the top. So I think of it the same way as 1 unit. So this is a ratio of 1 to 1.5. So these could be anything. I can make this 2 to 3. It's the same ratio.
Okay. And the same is true for column widths.
Column widths is a little different because the number 12 is still like important.
Okay.
But essentially, yeah, so this is 12, which means it takes up the entire first row. And then 8 plus 4 is 12, so that would take up the bottom row. Let's say we made this 6 and 4. So there'd still be 2 unit columns available.
Yeah.
That'll change the output, that there's going to be extra space that it shouldn't be filling. Yeah, so on the right side here, there's those extra 2 units, 2 columns that aren't filled. So you want to make sure that if you want to take up the whole space, it sums to 12, or you can add almost like a spacer here in between this table and this summary, and then have it be where the summary is on the right side, and we just have a gap in between so it kind of looks cleaner. So you would either do that or just make it so that it adds up to 12.
Thank you.
Hey Josh, like if you like change that 8 to a 9 and all of a sudden it has to become 3 rows because it's over 12, it'll throw an error, right? Unless you give it another row height to
I don't know. Let's see.
yeah.
It
No,
hasn't
yeah.
come over yet. I think it might have just moved it over and just went with the value.
So it looks like it's
Probably just went with
repeating.
1 again because it's just going to take whatever the base value is, I guess, in this case. Yeah. So if you're having issues with layouts, PDS lib, then just make sure things are summing to 12. Probably the simplest. Yeah. Okay. Any others before I go to the next app example?
This is one from Megan actually, and I sort of butchered the answer, but the new type operator you're using,
Mhm.
can you just sort of go while you're doing that instead of the pipe?
Yeah. So at this point, I'm working on our 4.3.1. So anything 4 and above has by default kind of built in a native pipe operator or base pipe. So the pipe that was traditionally used for a while that was available through dplyr, which was originally from a package called Madritter, but had like the percent sign, greater than percent sign. And now it's kind of convenient to just have something that's kind of in there by default. So if I don't use dplyr, I can still use a pipe without needing to install all of the other overhead for dplyr. So just trying to use one less dependency, even though I tend to use that package all the time anyway. But it does work slightly differently. So if you're familiar with using the other pipe, you could normally like use a function and then add like a dot to reference like the data set and then do whatever you want it to do. But for the base pipe, it doesn't do that or allow that. So some workflows that I've had like don't work if I've converted it. So just be careful if you do decide you want to switch the base pipe, that you make sure you like adjust things as needed. It definitely won't work one for one necessarily.
And is there like a hotkey like Command Shift M for base pipe?
I just changed my key shortcut. So instead of it putting the maturator pipe as my default, now if I do Command Shift M, it gives me the base pipe.
Oh, gotcha.
So same thing, you just need to go into your options for RStudio, but I can also change it back if I wanted to.
Yeah.
But yeah, same key shortcut. I just changed my default. Yep. Okay. So I'm going to go to the next example. So I have that stored in, we go back to the parent directory. So Intro to Shiny Workshop. Their spatial example. I have a set of scripts in here. There's one here that we're not going to actually run. But this is essentially a script for downloading and accessing the data that I'm going to be using for this example app. So I'm not going to be going through this example at all, but this is for your reference. I simulated like animal movement tracks. I downloaded sea surface temp data using this RERDAP extracto package. And then I have something else for showing that where I got the polygons from for actually file for wind lease areas. So I'm going to skip this because that's going to take up too much time and just move on to the first main script, which is one leaflet demo. So before I get back to Shiny, I'm not sure how many people are familiar with or have used Leaflet, but it's originally a JavaScript library package that people have converted for R. And it basically just makes interactive maps for you without Shiny or something like that. So you can make all these different crazy tools and just put them embedded in a R Markdown or Corda documents that people can access just without Shiny. So that might be a nice option, that if you don't need certain components from Shiny to just make a standard kind of leaflet map, and that might have everything you need and then require less overhead. You don't need like a dynamic server running stuff, computations in the background, and you could put it online somewhere like on a static website, which is more convenient. So I have a link here if you wanted to go to the Leaflet website. So this is the website, a lot of help info, different articles on making things. So this is a nice resource for kind of just getting started, and they have these maps embedded. Okay. So the packages I'll be using, in this case, I'm just loading the Tidyverse package because I'll probably use 3 different packages from it, like the per package, dplyr, maybe like stringr. So instead of loading them individually, I just load them all at once in case I need multiple. For raster loading manipulation stuff, I'm using Terra, which is an updated version that's faster than the raster package. So if you're used to doing spatial workflows in R using raster, it's now kind of unsupported and probably soon will be fully deprecated. So I would start shifting to either Terra or the stars package. SF is for dealing with vector layers. Same if you've been working with the SP package in the past, probably need to switch your workflow to SF. So that's right, points, lines, polygons in space. Then again, the leaflet package is for making the maps. LeafM I'm using for different kind of helper add-ons, extensions, to adding more components to leaflet maps. And then I'm using different color palettes from this Veritas package. So I'm going to load all these. And then I'm sourcing in a file.
Oh, no, we lost you, Josh.
Oh, okay. Where did I get cut off at?
just for when you're sourcing the libraries. It's pretty quick.
Okay, so we're just going to load all these different libraries in, and then on line 15, I'm sourcing in an R script, which basically means I'm just running an entire R script without needing to run it line by line from a different R file. So I'm giving it the file path here. So it's our base directory is the intro to Shiny Workshop, but we're in this subfolder called spatial example. So I'm giving it the folder name and then slash, take the note that it's in the subfolder, and then it's this utils.r script. And if you open that, it has a number of different helper functions that I wrote or repurposed from somebody else. But the only one we're going to be using for this example, if this scrolls fast, is add legend decreasing. So I'm adding like a custom add legend function for leaflet to make it look more like what I want instead of the default. So I'm essentially just loading in those functions, and you see those pop up in my environment here. Okay, so next component I've blocked off is just loading the data. I won't spend too much time on some of this unless somebody has a particular question, but the first part is I simulated some tracks like I mentioned. So I'm going to load that in from this data folder, which is in, you go back to the parent directory, a folder called data. That's where all these layers are stored. So I have that as stored as a CSV. So I'll load that in. And then in this particular example, I'm actually using this Madrider pipe. So I wrote this, whatever, a couple of years ago. So I still left that in there. But that's why we have this dot kind of notation here for the data set from the pipe. So I'm going to convert it to an SF object. So I'm using st as SF, which is converting this data frame from a data frame into a spatial layer. The coordinates are labeled X and Y. And then I'm saying that the projection here is this EPSG code 4326. So that's the default standard WGS84 if you're dealing with latitude, longitude. So if I run that and then print the output in the console, we see this is a simple feature collection as 5,005 rows or features with 6 fields or columns. It is essentially a set of points. It gives me the coordinates for the bounding box. And then again says this projection, which is WGS84. And the columns that are in this data set are the ID, the time, which is just sequenced 1 to 5,000 essentially. SL and TA are representing step length and turning angle. States is a value from 1 to 3. So these were simulated with a hidden Markov model. And then track length is just the number of observations for that ID. So this is reused from a different example, but the only things we really need to worry about are the coordinates and the ID in this case. So the coordinates now have moved from an X and Y column to a geometry column now as this kind of point spatial object for each row. Okay, so yeah, if we were to do head on each of these, that just shows what's in there. So originally it was X and Y, and then now it's turned into geometry. Sea surface temp, I downloaded monthly data for 2021, and that's all stored in a CSV file. And then the code here from lines 34 to 37 is just basically changing this data frame now of sea surface temp data into raster layers that are stacked across all the different months. So I can explain this more if somebody wants to know. Otherwise, I'm just going to kind of push forward. It's already 5:25 and just run it. But this is what it looks like. So we have it class spat raster. We have our resolution, dimensions, extent, all of that, projection. And then we have the names here, each of the different months, and our min and max values. One thing to be aware is if your names for each of these layers are character strings like this, it reorders them by like alphabetically. So either stick with numbers for each of the months if you're using months or day of year. If you're going to use character strings, just be aware of this as you're kind referencing them later if you're using like the bracket syntax for specifying the first object or second, third, etc. They'll have moved on you. And then the last spatial layer is this offshore wind lease areas for the Northeast US. This is just a shapefile. And we see here when it's loaded in, it's a multi-polygon geometry and same projection, WGS84. And if we look at the state column from this data set, we see that Massachusetts is listed twice. And that's because whoever put this data set online misspelled Massachusetts once, so they don't have one here. So we just got to fix that typo. And then if we were to run this again, we only have one Massachusetts that's spelled correctly. So we do that. But getting into actual like coding with leaflets, there's a large number of different providers for lease maps. So if I print providers, we have, I don't know how many there are, but just like a ton. So some of the most common ones you might have heard of if you're familiar with kind of interactive GIS mapping is OpenStreetMap or Esri or Carto. There's a bunch, MapTiler, there's a bunch of others, but those are kind of the big ones. So if we want to just create a map, the way you would do it is start with a leaflet function. We're just leaving this empty, and then we're piping to do all these additional functions to do stuff, to add things. So we're going to pipe this leaflet map. So if we were just run leaflet by itself, it should just be like an empty nothing in our viewer panel here. So that's where we're going to use this add provider tiles function. So we're going to take providers and then specify what provider we want to show for our base map. So if we only run that, it's going to show us the entire world. So at least we have a base map now, but what if we want to focus on a certain area? There's a couple ways to do that. One is to use the boundaries of a data set you're looking at. If you don't have a data set at the moment, you can set the view of your area, of your panel. So you specify the centroid, essentially, the center, so the longitude and latitude, and then you set the zoom value. And you might need to play with this to see what it looks like for the full extent. But if I use these coordinates and then this zoom value of 6, we have it kind of zoomed in here on the Northeast US. So this is going to be the main primary area of interest for this example I'll be walking through. And we can look at different base maps. So this is an ocean base map. So if I was to zoom in, we get some of these canyons, like the Hudson Canyon here off Long Island, New York, New Jersey. If we want to look at satellite imagery instead, we have this satellite imagery map where you still get a lot of that stuff. But what if you want cities to be labeled and state boundaries and all these other things? You can use, in this case, just the standard base OpenStreetMap. And now this gives us state boundaries, city names, essentially like the EEZ, all that kind of stuff. And there's plenty of other base maps you can look into. So these are just some examples. But now we need to add our spatial features. So the features that we loaded. So in this case, we're going to take our previous example, and then we're going to add this tracks data frame. Just showing again, this is a data frame. We're going to add that to this leaflet function, and that's all we'll need to put in there. We have our provider tiles specified as the base map. And then to add points, they're referred to for leaflet as circle markers. So it'd be nice if everything was similar to like syntax, like ggplot. But in this case, yeah, points are called circle markers. So that's what we're going to use here, is this add circle markers function. And we have to specify for our data frame the longitude and the latitude, which are, the arguments are labeled LNG for longitude and LAT for latitude. And since we have our data set kind of loaded in here at the beginning, the way we can refer to these column names is using the syntax of having a tilde and then the column name. So for the X coordinate, I'm having tilde then X, then the latitude is tilde then Y. If I do that now, this is what comes up for our point layer, which is by default pretty bad. Can't really see anything, especially when you're zoomed out at that initial zoom value. And this is the default coloring, styling, all that, which isn't great. So we got to go make some changes. But first, to show comparison, so that was using our data frame object of the tracks. In this case, on line 85, we're using the SF object. We just have that at the beginning as well. But for add circle markers, we don't need to specify the columns for latitude, longitude. It just knows where to look for that because it's a spatial layer. So we get the same exact thing, but now we're not needing to specify some of these other columns, and we just let Leaflet do that for us, which will be a lot nicer down the road once we're trying to plot like tracks and lines. It's not as bad for points. But what if we want to do some styling to actually make this look visible? We can use some different arguments within the add circle markers function. So in addition to the longitude and latitude, we specify the radius, and that's the point size. In this case, they call it radius. And then opacity is how we define the level of opacity transparency that's present. So since there's gonna be a lot of overlapping points, I'm gonna set the opacity to half or 50% in this case. So now it looks better. We can actually see the points. And if there's clusters of points, you can kind of tell that there's like a high density there because of this opacity. This is looking a bit better, but we can definitely improve on it. So what if we want to have the points colored by a variable? So in this case, the track ID, there's 5 different tracks for this data set. So what if we had the points colored by ID? You essentially need to create a color palette for Leaflet. And there's a few different functions for doing this depending on the variable type. So for factors, so anything that's kind of like a discrete value, you use the color factor function and then specify either palette name or set of values. So for palette name, it takes essentially any palette name from our color brewer, or most palettes from Viridis. If it's a new palette from like the past few years that they just added, those aren't available yet, at least by default in here. But if you just specify the name here or color brewer Viridis, it'll use that. And then you just need to make sure that whatever variable you're using is a factor. So in this case, ID is an integer or numeric. So I'm just converting it here to factor while creating this palette called TracksPal. And then I'm essentially adding on to the code before. So in addition to the other components for add circle markers, I have an argument called color. And then we get some kind of weird syntax here where I'm using this tilde again. So I'm pulling out the ID from the tracks data frame, but I'm wrapping it in this tracks.pal object we just created, because for all intents and purposes, if I print TracksPal in the console, it's just a function we created. So you're essentially running this function, and the argument is the column name. And we just have to make sure we specify the tilde at the front, otherwise it won't work. So we're adding this color palette to these points. And then if we want to, we can also add a label whenever we hover over the points. So same deal, if we're using a column name here, we have the tilde at the front. In this case, I'm using paste 0. You could use the standard paste function. You could use glue. You could use cat probably, that just add text together. So in this case, I'm adding the string ID and then giving the variable name for the column ID. And that's what's going to show up whenever I hover over a point. And then at the end here, I'm using the add legend function to add the legends. So we need to specify the palette, which again is this TracksPal object, the values shown next to the palette that it's mapped onto. In this case, it's the ID. I'm having that tilde at the front again, pulled from that tracks data frame, and then we just give it a title. So with that, now we have points that are actually styled and colored by ID. We have our legend at the top right here by default. And now if you hover, you get this kind of label that pops up showing the ID name and number. So this is great. This is already a lot of functionality and aesthetics that we need for a lot of different projects. with not a ton of effort, just like 10 lines of code here. But what if, for example, we wanted someone to have to click on the point or the marker to have a label pop up instead of it just showing up whenever you're hovering? Maybe.
Oh, Josh, I lost it.
It's computationally heavy.
Do we know what animals these on?
You say stimulated them, I think.
Okay.
But I don't know what they're supposed to be.
Am I back?
Yeah, you're back.
Okay. Yeah. Sorry for that. So what was the last thing I said before I cut out?
You're talking about the pop-up.
Yeah.
Yeah,
Okay.
sorry.
Make them
Yeah.
stay.
Yeah.
So in place of the label that I had before, the label argument, I replaced it with pop-up. So that just means you need to click on it for the label to show up. In this case, I'm doing the same syntax for showing the ID, but then also adding 2 new values for the longitude and latitude in case we're interested in that. And this is essentially the way you would need to do labels for adding multiple rows or multiple values. So it's not just all on a single line, is you're using essentially like a HTML tag. So in these kind of less than equal, less than greater than signs, that's kind of like bracing in the tag. And in this case, I'm using BR, which is a line break. So that's saying that I want a new line before longitude and a new line before latitude to show this pop-up label. But otherwise, everything else is the same. Nothing else has changed. So if I show it, again, the map looks exactly the same. But when I hover, nothing happens. If I click, then we get ID, longitude, and then latitude printed on separate rows. So there's way too many decimals here. You can always like, round this if you wanted to. But we'll at least have something that's working now, giving us some more functionality. So that's it for points. Are there any questions about the point stuff before I move on to line objects?
You're putting in your own color values. Do you need the same exact number of values as the number of things you need, or can you have more?
You could potentially have more. So like if you specify your palette and your palette has like 15 values, but you only have, in this case, like 7 tracks, 7 IDs, it'll just take the first 7. But if you specify more like factors, more values than there are palette colors, then that'll be a problem where I could just won't show the other stuff. So you would need to like either custom like add your own colors to make your own palettes, or you essentially just append one palette with another palette with another palette, which is what I've done in the past when you have like, I think I tried plotting like 100 turtle tracks and I wanted them all to be different colors roughly. So I just needed to use like 8 or 10 different palettes. I think I was using like the Wes Anderson package for using like different palettes. But you just need like mishmash stuff together potentially. Because otherwise it just won't show up. Okay, so for lines, it shouldn't be too different, but to show an example of how the syntax compares for using a data frame object versus an SF spatial object. I'm going to create a new object here of just palette colors, same as before, but just instead of a function, now it's just like the actual hex codes. And what I'm going to be doing is creating a base map that's going to be stored in this object called new map. So it's just going to be an empty map with the base map on it. But what I need to do if I'm using a data frame essentially is to like, use a for loop and have it each time add a new line like track layer and then reassign and like overwrite the map object. And for whatever reason, it didn't used to be like super computationally intensive on my computer, but then it just all of a sudden is. So it didn't take too long to run. I feel like I've had to wait like 10 seconds before for it to finish running for this exact example. But then if I plot it, it takes a while to like render and show up in my viewer pane. And if I try to zoom, it's gonna be really like slow and laggy. Yeah. 3, 4, 4 seconds just to zoom once. So that could be the code, or it could just be something else with how that's made. Remove that. But if you're using SF instead, it's just easier. So you would take your SF object, which is originally what we made as a point object. And if we want to make an individual line or track per ID, I'm going to use group by ID. And then you would need to do summarize, which is like the same as the dplyr syntax. And then in this case, use this argument do union and set it to false. Otherwise, it's going to like basically put all the different IDs together into a single line path. And then we're going to change it from points to a line string, so like a line or a track. So if I was to only run this first part, we see that there's a single row per ID, and each row for the geometry is a multi-point object of all the coordinates as points. If I include the stcast part at the end, and then print this in the console, now we see that it says multi-line string instead. So now it's going to plot it as a line instead of a set of points. So for this example, you would just add that to the beginning for this leaflet function, and then essentially like, that's it for the hard stuff. You don't need to make a for loop. Again, I'm just specifying the color here from that tracks pal object for ID. I'm setting the opacity here to 0.75, so it's a little more opaque than the points I made before. If you want to change the line thickness, you would use the weight arguments. And then I'm adding a label here, again, as I did before, and a legend. So that would look like this. So we get our labels when we hover, and then it zooms in without much of a delay. Okay. Moving on to polygons. It's not that much different than what we've already done essentially at this point. So I'm going to create a new palette for the polygons using, again, color factor. And I'm using this set3 palette from Color Brewer and coloring these polygons by state. So we have this new palette I call polypal. And then I'm using the wind SF object. And to add a polygon, you do the add polygons function. And again, you would specify like color here, and you label the palette the same way. So tilde, name of the palette, in this case, polypal, and then state. And then I'm making the opacity fully opaque, so a value of 1 or 100%. Turning off the stroke, so there's no border in this case, setting it to false. And then I'm adding a label for the state name. And then again at the end, adding a legend. So now we get a set of polygons showing up along the East Coast here, going from Massachusetts all the way down to North Carolina. And it just says the state name associated with each of these. And that's it for polygons. And then moving on to rasters. This is the last spatial layer type that I'm going to cover. So adding a raster layer could be really easy. For example, just these 3 lines of code. So we're initializing our leaflet map, adding the base map, and then adding the raster layer using the add raster image function, and then specifying a single, in this case, raster layer object. So in this case, sea surface temperature for January of 2021. And that should be all you need to do. And we get pretty map. The kind of issue with the defaults here, though, is that in this case, red is representing the lower values, the colder water, and blue is representing warmer water for January. So it's not exactly intuitive, and this particular palette has some weird kind of like breaks here in the color where it looks like this light yellow stands out, which that might not really be anything in particular. It's just an artifact of the palette itself. So we want to kind of make our own custom palette and add that here to make it a bit nicer. So since we're using a numeric value, a numeric scale, instead of color factor, we're going to use the color numeric function. And then from Viridis, I'm going to specify I want the magma palette. And then I'm setting the domain or the set of values that should be represented by the palette. So I'm using the values function from Terra to basically list all of the values from this raster layer. And then if there's any missing values, I'll just have them be represented as transparent. So I'll create that palette. Essentially, this is the same code as before, but now for add raster image, we specify colors as raster pal. That's all we need to do. We don't need to do anything else, essentially, like we had to do for all the vector layers. And we're setting opacity to 0.8, so 80%. For add legends, we're adding our raster palettes, adding the values from that raster layer. And for title, sea surface temp, I'm using some Unicode here to give me that degree symbol. So that shows up. And now we have something that looks a little bit nicer. So we actually have cooler colors representing cooler water temperatures and warmer colors representing warmer water temperatures. And you see that the warmest temperatures here follow along what should be the Gulf Stream. So that makes sense. That's intuitive. And we lose that artifact here that was kind of in between the Gulf Stream, kind of where the continental shelf was. So that's good because that means there's probably more of an artifact to the color palette. But one thing that bugs me with this particular map is the legend, because by default, the leaflet legends for numeric values always are like ascending. So they start at the lowest value and then the highest values are at the bottom, which is not really what it is by default for almost anything else. So if you want basically the legend flipped, there's not many options out there. So I found on like a Stack Overflow forum, like a page of a modified function someone created essentially. So all you would need to do is from that script I sourced at the beginning, it added this add legend decreasing function. And the only change here from the previous code is I have a new argument called decreasing. So I can set this to true now. And that way the values will start at the highest value and then decrease as you go down. So now I feel like that's a bit more intuitive for reading this map and the legends. So we have the highest values of temperature at the top, the lowest values at the bottom. And then I think I have at the very end of this script just a few examples of just other things you can add. So I'll show here how you can add multiple raster layers and then other kind of widgets that look nice. And we're running out of time, so I'm going to try to go through this really quickly, but we are adding multiple base maps here. So I have an ocean base map, world, so satellite imagery, and then kind of political boundaries. I'm specifying how these can be controlled and what their names are, as well as different spatial layers I'm going to put on top of the base map. Adding these raster layers separately. So I have a raster layer of temperature for February and one for August. And then I have these add image query functions that are from that leafm package. And that basically lets you kind of hover over the raster and it'll print out what that raster value is on the map, which is really nice. We have our add legend decreasing there for making the legend nicer. And then we're adding all of our other spatial layers on this. And at the end, there's a few other helper widgets that are nice. So adding a scale bar, which dynamically scales depending on the zoom, adding a measurement tool if you want to measure distances or areas, and then adding mouse coordinates and zoom value. So wherever your pointer or your cursor is, it'll tell you what the coordinates are. So if I run that doesn't help. Make that bigger. So now we have our raster layer here. If you look at the top right, we have the values showing up for August and February. If I go to the bottom left, here's all of our different controls. So I could change the base map to whatever I want. I could turn off August, and now we see February. I can add August back. I can remove the tracks. I can remove the wind lease areas. You can do all kinds of stuff here. And this is only with leaflet. I'm not even using Shiny right now. We have the mouse coordinates at the top, all that stuff. So that's great. But what if we want to put something like this in a Shiny app where we have some more flexibility in what we can do? Well, I'm going to open up the second script here, restart R again. And I'm using the same packages. I'm loading this the same way. I'm just run all of this stuff. And so this is now going to be a Shiny app. And kind of one thing I didn't show in the previous app, since we only had that simple single data set, is if we're reading in or loading in these external data sets, we essentially want to do this with like loading all the data at the very front. So we're not going to load the data in the user interface or in the server. So that's just going to add more overhead that just makes the app slower and has to reload it constantly when it's not necessary. So you want to load all of your data outside of the app at the very beginning. And now I'll go into the R environments. And then we're going to create a really super simple user interface. So I'm just using the fluid page function from Shiny, the Shiny package, giving the app a title, and then using leaflet output to show the output of the leaflet map, where the ID for this map is called my map, and I'm specifying the dimensions. That's it. There's no other component to this user interface. It's just the embedded Shiny map, or leaflet map. The server side is just all the leaflet code wrapped in that server function. And now we're using a render leaflet function stored in the my map variable of the output. And that's it. So essentially, there's nothing really to this particular app, because you could essentially have all the same functionality without Shiny. Because in this particular example, you don't need Shiny at all. There's no Shiny component that's helping you in this case. So this is an example of where Shiny isn't even necessary at all. But just wanted to show you that you could basically make this map without Shiny, and then this is how you would start adding it into these different sections. If we were to now add, let's say you wanted to change the month of the raster layer, instead of only showing the 2 raster layers at a time, maybe you want to filter what's being shown so it's not so messy. You want to add some inputs so you can do some filtering. So now we're going to add this kind of additional complexity into this other app. I have, I think, 1 or 2 new R packages here. So the Shiny widgets function or package I'm using to add a different widget. And then now I have kind of the sourcing in for that helper function. So if I was to try running this just straight within the R script, it's going to give me an error here that this utils.r file doesn't exist. If I try loading in the tracks, it's going to tell me that this doesn't exist, it doesn't work. And that's because once you're running a Shiny app with external data, it's looking for the data in certain folders or certain directories. So if you're running it interactively within the script, instead of pressing like the run app button, it's going to assume that whatever is shown kind of here at the top of your console is your working directory. But whenever Shiny is looking for files, it's looking within whatever folder or directory the Shiny file is in. So this file is in the spatial example subfolder of the Intro to Workshop folder. So it needs to know or figure out where to look for these files. So utils.r is actually in the same folder. So that's fine. It doesn't need to look anywhere else. So we're going to leave it like this, essentially. We're saying it's the same folder, so just look adjacent to you. But for the data, we have to go up a folder. So that's where we're using these double dots for. Means go up to the parent directory and then go in the data folder. And then it's the simulated tracks file in the data folder from a separate directory. So that's where it's actually going to look for these data files. So that's how you need to specify it. But yeah, it'll throw you an error sometimes if you don't have the right directories in place. So if I just hit the run app button, it'll work without screaming at me. But now we have a map with a single raster layer. We have polygons that we can filter. So let's say we want to remove Massachusetts. Massachusetts is gone. Let's remove Maryland. Maryland's gone. Remove New Jersey. So that's all updating nicely. Let's say we want to change this from January to July. Now we have a raster layer for July for sea surface temp. Let's say we want to remove certain tracks. Those will change. So all that's good. I need to zoom out of this so it actually shows. It's not working. Shows the widgets at the bottom for changing the base maps, but yeah, it's not letting me resize it at the moment. Oh, there it goes. So we can turn stuff off. We can change base maps. All that's still available to us. And the biggest issues or hurdles with doing that is, I'm going to skip a lot of this because we're almost out of time, but I'm essentially adding in that panel of inputs using absolute panel here instead of a sidebar. And I'm using draggable so we can move it wherever we want it to. I have a leaflet output here for placing or adding in our output of our leaflet map. And then here's all the input components for that panel. So our different widgets, we have 2 picker inputs for the tracks and the polygons. And for the raster layer, we're using a select input for a drop down for sea surface temperature. And that's all the stuff in the UI. And the server for leaflet is a bit more complicated. So at the top here for the server function, we're creating a set of reactive objects. So we're allowing the reactive function to filter the tracks by the ID, the wind shape polygons by the states, and the raster layers for sea surface temp by the month. So that's what's shown here at the top is these 3 reactive objects. And then what you have to do for creating the leaflet map outputs is you essentially create like a base map. So you add all the components that aren't going to change at all based on these reactive objects. So that's only going to be here. I'm setting the view of like the extent panel, adding the base map layers and the controls, and then like the other widgets like scale bar, measuring tool, and mouse coordinates. And that's all going to go into this my map variable for the output. So that's under render leaflet.
Oh, Josh, we lost you.
So you have
You
your
cut out.
go ahead.
Oh, you cut out when you were explaining the render leaflet.
Okay.
I don't
Yeah.
know the base maps.
We have the reactive objects. Then for render leaflet, this is our base map essentially. So all the stuff that's not going to change goes in render leaflet, which is what we had before for our simple example. But you leave out all the stuff that will change with the reactive objects, and those are going to go into different elements. So instead of reactive, we now have observe. So observe is going to look for changes in different reactive inputs, essentially. So we're going to wrap it with the parentheses and curly braces. And instead of just leaflet, we're going to start off with leaflet proxy. So the leaflet proxy is what's going to look for updates to the map. And we give the map ID my map, which is what we defined as our kind of like base map, static map for the initial outputs. And this means that we want to adjust this initial version, the original version. And typically you want to clear all the different components because otherwise they're going to continue to stack on each other. And that could be a problem because it just makes everything messy and you can't see all the different layers that continue to be added. So we have clear markers for like clearing points, clear shapes for clearing polygons, clear images is used to clear raster layers, and clear controls is for like any other of the controls being used for like the view extent or the input or something else with layers turned on and off. So we want to reset all of that and then add our new components. So we're going to add the raster image. And again, we're using a reactive object. So we have SST out as our reactive sea surface temp object with open parentheses here. And that's going to mean it's a reactive object. give it our palette, all the other info, and then we go ahead and do the same thing with the other reactive objects. So for the wind lease areas, we're doing the same thing with our reactive object here, wind out. And then for the tracks, we're using tracks out for reactive objects. And then we close that observer and we close the server. So now if we were to run this, we should have a Shiny app that's a bit, nicer to work with compared to kind of the original version that didn't need Shiny. And just to show that once your apps get more complex than this, like this is only 200 lines, they can get up to like 800 lines or something, 500 lines. It gets really messy. So you might need to break it up into multiple files. So in this case, my example is I have all the packages being loaded and the data being loaded in one file called global. And then I have my server and UI components in their own separate files. And these names are pretty important also, UI, server, and global. So if I was to have global, I can hit a run app button will appear. And now instead of having a single like app.r file, I have multiple files that are a little bit easier to work with. And for this example, I wanted to show that you can use a button. So if I want to select the month, let's say it's June, I'm going to include all these polygons and tracks and then hit update map. And then it'll add it and make the change. So if you're doing something that's really computationally heavy, it might take a while to render and load with each filter change. So you might want to have the users have to press a button before it'll make any changes. So here's one example of kind of including a button. But that does it for the examples